Hi everyone. My name is Matthias. I'm a PhD student in a group of Albert Boman at AMOF in Amsterdam, the Netherlands. And it's my pleasure today to talk about a project in which we have a slightly different approach to metasurfaces than is maybe known to many of you. And that is to use free electrons, in fact, to drive metasurfaces, and thus use metasurfaces to control the interaction between free electrons, light and matter. This is a project I'm working on, not on my own, of course, but with fantastic collaborators, in fact, from within AMOF and Tel Aviv University, Technion in Israel, and our partners from TU Delft, also in the Netherlands. Now let me get my laser pointer over here and let's get started. So first of all, I want to introduce this talk with the question, okay, why are free electrons relevant to nanophotonics and in essence then to metasurfaces? Well, in fact, a free electron, if we look at it over here in this cartoon, it can drive a nanophotonic structure such as, for instance, this plasmonic nanotip here in a very similar way to an ultra-short optical pulse. So as the electron passes by our nanotip, you see in this video, it actually takes, depending on the electron energy, it just takes a couple of 100 attoseconds to femtoseconds to pass by this tip. Now, that means if we take the Fourier transform of the electric field, the electron itself exerts now on our nanotip, we see it has a huge spectral frequency content. And now that means it can polarize our nanotip at all kinds of different frequencies and thus drive certain resonances in the material. The electric field that is associated with this induced polarization again acts back on the electron, and that causes it to lose a certain amount of energy, which then upon de-excitation of the induced polarization can be again re-emitted as a photon into the far field, and that's called cathodoluminescence, or in short, CL. Okay, well, this interaction is exciting now for metasurfaces. If we look at such a periodic structure here, we have a grating, regular grating. If now an electron passes by this grating, it consecutively excites those grating bars, and you can think of them as dipole emitters essentially. So it drives those dipole emitters with a certain phase lag that is determined by the electron velocity. Now in the far field, now the dipole emitters, they radiate and emit into the far field, and in the far field, this radiation of a given wavelength can interfere only under specific angles in a constructive manner, which means, in fact, experimentally, we can observe only for a certain emission angle, we can only observe a specific wavelength. And this is known as the Smith-Purcell effect, or Smith-Purcell radiation, described by this equation over here, where m is the diffraction order of the radiation and lambda is the grating period. Now, we studied this experimentally in a scanning electron microscope at AMOF at an electron energy of 30 keV. That's roughly 1/3 of the speed of light, is the electron velocity. And we were having these electrons graze this grating structure. And we measured now the emission spectrum of the radiation as a function of the emission angle. And you see this nice curved dispersion relation is typical for the Smith-Purcell effect, which is represents exactly what I just described. We have a unique emission angle per emission wavelength. Now, together with our collaborators from Tel Aviv University and Technion, we were wondering, well, the Smith-Purcell effect, in fact, is exciting because you can generate with your electron in your structure radiation in all kinds of spectral regimes. In fact, you can enter the terahertz regime, you can go into extreme UV radiation and even X-rays. And you can alter that tune just by the grating parameters in your electron velocity. But it's in fact kind of plane waves which are emitted by this grating. And for practical purposes, it would be now exciting if we could actually shape the wavefront of this Smith-Purcell radiation. Interestingly, so this has been studied theoretically this far, it is possible, in fact, by using metasurface design principles, so we can tailor the periodicity of our grating. We can induce a local grating period which varies along the electron trajectory, and thereby basically implement any emission wavefront phi that we want. If we use, for instance, spherical wavefronts, we can thereby introduce a focusing effect. So we can emit spherical wavefronts which interfere constructively at a certain focal spot at a distance f away from the grating surface for a particular nominal design wavelength lambda naught. So we have studied this now theoretically using a numerical finite difference in the time domain simulation. So after plugging in our expression for the spherical wavefronts, we obtain our design recipe for the corresponding grating period, where here the plus and minus signs give us a negative chirp along the electron trajectory and a positive chirp respectively. And now performing simulations for these two different structures, we in fact observe for our nominal design wavelength at 580 nanometers. This nice focal spot here around 17 microns away from the grating plane on the left. And for the diverging structure, in fact, we have diverging wavefronts emitted away from the structure with the virtual focus here at the equivalent distance behind the grating plane. All right, now to study actually this lensing effect experimentally, we again went back to our scanning electron microscope. We fabricated a converging and diverging meta lens according to the design recipe I've shown you on the previous slides for, again, the 580 nanometer design wavelength. And in our scanning electron microscope, we have it equipped with a parabolic light collection mirror, which features a small hole where the electron beam can pass through. We've mounted those samples vertically underneath the mirror and then collected the light emission with the mirror, guided those light through an optical imaging system to project it on a spectrometer where dispersion grating then disperses the light on a CCD sensor. And this allowed us to do those measurements we see here on the right for the converging and diverging meta lenses, the far field emission profile of our structures as a function of the emission wavelength and emission angle. Now you can see these complex oscillation patterns that we observe here with a similar curvature as we have seen it for the regular Smith-Purcell dispersion, but now over a broad spectral range. And okay, to understand these complex emission patterns and also correlate them, of course, with the desired near field effect, so this converging focusing effect or diverging effect, we performed a hybrid approach simulation. So we used our FTDT simulations as a source for then a ray tracing model of our experimental light collection setup. And as you can see, we find a really nice agreement here between the experimental and the simulated data. Now we also took a profile along those red dashed lines over here, profile through those spectra as a function of the wavelength for a fixed emission angle to nicely resolve those oscillations we observe both in experiment and simulation. And those oscillations in emission patterns, they are in fact reminiscent of the spherical wavefront curvature. So the spherical waves emitted along this grating interfering in the far field give rise to these complex oscillatory emission patterns, which yield us in that sense an indirect proof for the desired near field effect of lensing near the structure surface. All right, so now I've given you some proof here that we can in fact prove that we can affect shape Smith-Purcell radiation. We can, interestingly, we can take this now a step further by considering such a 2D split ring resonator meta lens surface. Now, we compose it of the split ring resonator atoms, and we again tune the spacing of these arrays here in the horizontal direction for the electron trajectory. And this allows us to again induce a focusing effect of the radiation emitted by those split ring resonators excited by the electron beam. However, because our electron beam allows us to locally excite our structures with nanometer precision, we can now tune also the polarization of the radiation by exciting basically different optical modes in our split ring resonators with different dipole momenta. We can access this perpendicular polarization here, which is forbidden in the regular Smith-Purcell effect. So we studied this in simulations, analyzed the polarization state of our light, and we actually find if we excite the split ring resonators here at the open end, we obtain a considerable contribution of the perpendicular polarization. And analyzing also the Stokes parameters on the Poincare sphere, we find that in this case, in fact, we have elliptical radiation emitted in the focal plane of our polarization tunable split ring resonator meta lens. Well, now, okay, we have seen we can shape the radiation, Smith-Purcell radiation with meta surfaces. Now we were wondering, can we also do it the other way around. Can we use light and metasurfaces to shape electrons? And yeah, in fact, this is something we can do, and this has been done first by Bavek et al. About 10 years ago. That if we now excite our structure with a laser, okay, let's look again at our cartoon here. With a laser and excited on resonance, we can induce a very strong near field. And if we then let an electron pass through this near field, the electron can in fact undergo stimulated emission and absorption processes. So they can pick up energy from this near field, also be stimulated to emit into the near field at the photon energy h bar omega of the pump laser. So we've recently studied this together with our collaborators from Klaus Rope's group in Göttingen, where we have in fact illuminated such a plasmonic gold nanostar here with a laser, and then measured the energy distribution of the transmitted electron beam, and found these side bands occurring here, which correspond to the stimulated emission absorption of photons by the electron. In fact, and a single electron passing through this near field undergoes all these processes with a certain probability. So it's literally walking up such a quantum ladder of energy states, which results in a modulation of the electron wave function. And well, this is a very interesting effect because you can modulate your wave function. You can basically split it up into ultra short wave packets if you want. You can imprint quantum information on your electrons. And this is fundamentally a highly interesting approach. So we were wondering in the course of this project, can we again apply metasurface design principles to gain more control over this interaction to make it more efficient? So we came up with such a layer geometry here. You can think of it as a Hall array perforated in a multi-layer stack of alternating metal dielectric layers. And now if we illuminate this with a laser from top on resonance, we can excite such plasmonic modes which live inside those dielectric layers, confined in between the metal layers. And they give rise to a very strong optical near field that leaks into the hole. If we now send electron beam through this hole, we can achieve a very strong efficient interaction with this near field. In fact, let's look at it from a mathematical perspective. Over here, we have our coupling, electron-light-matter coupling beta. This is a parameter that determines this energy modulation I've shown you on the previous slide. And you see, okay, it depends on our electric near field distribution along the direction of the electron trajectory, in this case, the z direction. So this is the near field component which exerts a force on the electron. And this exponential term over here, which basically describes the temporal oscillation of the field as the electron passes by with a certain velocity. Now, interestingly, we can identify this as the Fourier transform of the optical field at a given spatial frequency q, which is determined by the electron velocity and the optical frequency of our pump field. And accordingly, we can now tune basically the periodicity of this field in such a way that the electron interacts in phase with this optical field and thereby boost the contribution of this Fourier component to the field. So let's look at this rather complex color map over here. So I want to guide you through it. Well, we have on the right-hand axis, we have here the electron energy plotted, and the position of our electron beam passing through the hole, where 0 corresponds now to the center. And you see as a color code, we have here the encoded electron near field coupling strength, in this case, squared. And you can see now for our design electron energy that we assumed in this case, at 5 kilo electron volts, we obtain a nice maximum inter-interaction strength. What I also want to emphasize is that, in fact, you can see because the electrons become relativistic above a certain energy, their velocity hardly changes anymore. That means at several hundred kilo electron volts, like used that in a transmission electron microscope, for instance, your electron velocity approaches slowly the speed of light. You change the energy, but hardly you vary the electron velocity. That means you don't have that flexibility in choosing a wave component or matching your electron velocity to a structure, and thereby enhancing this interaction strength. While in a scanning electron microscope, where we can access those non-relativistic energies, we can largely tune the electron velocity and thereby adjust, first of all, the electrons to a structure, and also the other way around, exploit different geometries with different dimensions and still achieve strong coupling to electrons in an electron microscope. And in fact, we are therefore at the moment, together with our collaborators from TU Delft, developing such a setup where we can use our parabolic light collection mirror to focus a nanosecond pulse laser on our sample. At the same time, then place some interesting metasurface geometries there as I've shown in the previous slide, probe it with the electron beam, and measure the energy modulation of our electrons with such an electrostatic retarding field electron energy analyzer. Well, this is just as an outlook, so we are now ready to do those experiments, and I hope that by the next time I can show you some exciting results on that. With this, let me conclude. I've shown you the concept of a source-embedded Smith Purcell meta lens, where we use meta-surface design principles to shape free electron radiation. We can expand this concept and design tunable radiation sources. In this case, I've introduced you in a polarization tunable split ring resonator meta-surfaces, where we exploit the fact that with our electron beam, we can locally excite those, or spatially selectively excite those meta atoms with nanometric resolution, which is not possible, let's say, with an optical excitation source. I've shown you that we can use meta surfaces to shape now the electron wave function, and that in the future we are going to study this with our new development in the lab and quantum scanning electron microscope. With this, I want to thank you for your attention. And of course, I want to acknowledge again all my fantastic collaborators in this project. And I hope to get in touch with you. Feel free to shoot me your questions by email. I'm looking forward to the discussion. Thank you very much.